Good evening, everyone. My name is Lorenzo Rodriguez, and I'm a member of Team Helo. I am a double E here at UT Tyler. The other double E is June Gao. Our two mechanical engineers are John Hinken and David Kim. Our product design is the Quadcopter X. Our project statement was to design and construct a radio-controlled quadcopter that is capable of carrying a 1-pound payload and is targeted for hobbyist users. Quadcopters are becoming more popular amongst various groups such as military, engineers, researchers, and hobbyists. The popularity of the quadcopter has made it both expensive and very complex with all the added features and regulations. We've decided to refocus the use of the quadcopter and create an affordable device with basic flight maneuvers for simple use of entertainment. In addition, our device will have the ability to lift a minimum weight payload of 1 pound for third-party attachments such as GoPro cameras. Our goal here is to reduce the cost and remove the complexity of the quadcopters that other companies currently sell. Quadcopter X is just one of many competitors who produce and sell quadcopters with similar functions in addition to other extra features. For example, the DJI Phantom is one of the most popular quad or drones that you can have available on the market. It has an onboard high performance camera with a control that can record videos and take photos using an iPhone as a display. It is controlled using an FM transmitter and has about 25 minutes of flight time with an overall weight of 2.5 pounds and has an HD 720p camera. The other one is the AR drone. It comes equipped with the HD 720p camera as well, and it has ability to record video and take pictures as well. It is advertised as a quadcopter to be controlled by Wi-Fi using a smartphone or a tablet. So again, Quadcopter X, here our objective is to develop a quadcopter that is affordable with at least 15 to 20 minutes of flight time and ready for use right out of the box. So we want to reduce the cost and complexity of the use that anyone can enjoy flying a quadcopter without electrical and mechanical proficiency. So for our quadcopter design, we decided to use the Arduino hardware. As you can see in the image, this is an image of our initial prototype that we did. The red little chip on the right is the motion processor unit, which contains the gyro and accelerometer used for stabilization and to control the yaw, pitch, and roll. The MPU 6050 here, you can see we used a Arduino Uno shield to clean up and reduce the wiring. So the only wires that are left are truly the 4 wires or 4 connectors from the electronic speed controllers. This is a basic block diagram of our electrical hardware. We start off with the battery, which is a LiPo battery of 11.4 volts. We have the flight controller board, which is our Arduino board, and the gyro and accelerometer, which is the MPU 6050. The flight controller has the processor board and the receiver module. To the right, we have the 4 electronic speed controllers and the 4 motors. This is our RC controller that we purchased to begin our initial prototype. This provides a post position modulation signal to control the roll, pitch, yaw, and the throttle. It's a 4-channel RC controller. This is the output of the transmitter receiver that the Arduino Uno receives and interprets these signals into the speed of each motor individually. So you have 4 signals simply showing the control of the 4 outputs to each motor. This is the communications protocol that we're using. It's an I2C communications that is used for the motion processor unit to communicate with the processor on the Arduino Uno And as you can see in the image, everything I simplified it a little bit easier. The yellow channel is the clocks. The blue channel is the data that's coming out of the MPU that is going to the Arduino, and the Arduino is using this data, which is going to be again your X, Y, and Z for your gyro, and your X, Y, and Z for your accelerometers. And this is getting sent to the Arduino and being processed to stabilize the quadcopter. Jun Gao will take over from here and do the electrical hardware.
Hello everybody, my name is Jun. I'm gonna talk about the electrical hardware. So as Lorenzo mentioned, we're gonna use the Arduino Uno to control our quadcopter. And for the quadcopter, we always want to know what's the position the quadcopter and in order to stabilize the quadcopter. So the device we using to get all the data is the MPU 6050. It is a motion processing unit. It is a 6-axis motion tracking device designed for low power, low cost, and high performance requirements of customer electronics. For the MPU 6050, it contains a 3-axis gyro and a 3-axis accelerometer. For the quadcopter, it can work with the gyro by itself, but the gyro will be drifting if we don't have the accelerometer to give the data to adjust the data. So the MPU 6050 will give us the raw, pitch, and yaw. All these will stabilize the quadcopter. Now let's talk about how the gyro and accelerometer get the data. So both of them, they are measuring the angle changing to the axis. So for the gyro, it measures the angular velocity to compute orientation. But for the accelerometer, it plots orientation by measuring the gravity force. And for the MPU 6050, we need to calibrate every time before we using the quadcopter. It's just easy, like you just put a quadcopter on the ground, anything like flight, and power it up, and it's gonna be automatic calibrate itself. The next thing I'm gonna talk is the ESD, which is the electronic speed controller. The part we are picking is multi-star. This is the best choice for us because the cost is kind of low, and the maximum current for this ESC is 20 amps, which is way enough for our quadcopter. And the electronic speed controller can provide electronic 3-phase electrical power output to control the speed of the motors. And also one of the most important part is the motors. So we did some thrust tests for 3 different kind of motors, and we find the best one for us is the multi-star 2216, which is the green one. This is very good. It can provide a 780 gram per motor at full speed, which means if the 4 motors, it can go around 6.8 pounds, which is way more than what we require. And also, it compared the others, it will consume less current, which can make our battery last longer. So now let me talk about the most important thing for the quadcopter is the PID closed loop controller. So for the quadcopter, the stabilization system is the key part. So we are using the PID controller. The PID controller is adjusting the setting point to the output. So we want the quadcopters flying in certain speed or turn right, turn left, but it have an arrow between what we want and where is the quadcopter at. So this closed loop can adjust it by using the proportional, integral, and derivative three part of feedback. And there are three key coefficients, which is Kp, Ki, and Kd. And for PID controller, different cases is different. But for the quadcopter, the really key coefficient for us is the Kp, which is the proportional one. And we will be the quadcopter will be fly without considering Ki and Kd. But if you want the quadcopter be flying smoother, you can working on the Ki. It will working better, and the Kd is the rate of the changing rate of the quadcopter, which is not that important in this case.
Hello, my name is John Hinken, and I'll be starting off with our mechanical concept. So for the mechanical side, we had three main objectives we were trying to meet. We first needed to minimize weight, provide enough area on the frame to attach our flight electronics, and build a strong, durable frame. So we wanted to minimize weight to increase our flight time because there's an inverse relationship between weight and flight time. This is due to the less weight the quadcopter has, the less power is required from the motors to lift it through the air. So decreasing our weight also increases our flight time. In contrast to that, we also need to provide enough area to attach our flight electronics. Our flight electronics are what allow our quadcopter to fly around on its own without any type of tether. But we need to provide enough area, which increases our weight. So we needed to balance these two objectives to provide an optimal solution. The last thing we needed to do was build a strong, durable frame because we wanted to get multiple flights out of our quadcopter. Our quadcopter needs to be able to survive incidental bumps and rough landings. We also needed it to not deform if it did bump into something, so that the flight computers don't malfunction because a motor isn't where the computer thinks it's supposed to be. And we also needed the frame to be durable so that the propellers don't strike each other and break, and then the quadcopter falls out of the sky. We also wanted to take advantage of the decreasing price of 3D printers and include some 3D printed components to maximize our do-it-yourself attitude. Another objective was to have a symmetrical frame to make it easier to program our flight controller by having the center of gravity located in the center of the frame to maximize our stability. We also wanted a bit of a neat appearance by having wires contained, that is, having no exposed wires. So we wanted to run wires running from the motors to the electronic speed controllers run through tubes inside of the frame. The last secondary objective was we wanted an X orientation as compared to the plus orientation. The X orientation is where the front side of the quadcopter is located in between two adjacent motors. The plus configuration is where the front side is in line with one of the motors. We wanted the X orientation because if we wanted to add like an attachment, like say a camera, a motor wouldn't be in the way, like in the camera's field of view, for example. In the corner you'll see our initial design concept, which was really just a plate attached to some tubes with motors and some sort of 3D printed motor mount on the end. And we needed to take this concept and refine it, which leads us to our prototype design. So what you see here is our refined concept where we reduce the plate into a octahedral shape while removing a lot of the unnecessary area that we needed, while also redesigning the motor mounts to both decrease weight and combine some components together. We also needed some way to protect the flight computers from weather such as rain, so we added an extra shroud and also increased the area in between the plates to provide more room for electronics. To go into more detail for our prototype, for the specifics of our prototype design, here's David.
Thank you, John and helo team. So, how do we come about our final design concept? Well, we started with our initial size constraint of 18 by 18 and 12-inch height. The height was not too, it's fairly negligible since we weren't thinking to go more than 6 inches of material as far in the vertical plane. As far as the plane and the surface to the earth, we were looking to extend as much of the area as possible. So in order to maximize the area affected by lift, which is basically the route which is traced by the propeller shown in the figure, we went with the 8-inch props, and with our given dimensions, we would have 7-inch long rods, and depending on our faceplate, roughly keep it in more or less the 18 inches, but for coefficient figures and also for finalizing our stabilization, that actual dimension may be subject to change, but we can go ahead and put everything back into the original constraint if need be. As far as the propellers are concerned, we went with the widest profile blades that we could find. These 8-inch by 4.5 pitch carbon fiber blades. We found the ones with the widest profile in order to maximize the lift that would be generated as far as carbon fiber is concerned, because it is more brittle and rigid. It is able to have less resistance or prone to bending when it is in revolution, and also of course, the downside is that because of its brittle nature, any sort of impact would probably result in catastrophic failure. Of course, the carbon fiber tubes that we have, as mentioned before, are 7-inch long with a 12mm outer diameter, 1mm thickness, clamped to the frame using aluminum rod with pitch in between to reduce the jarring or any sort of vibration. And of course, we went with carbon fiber, which again will increase the rigidity, making our quadcopter in essence more durable, but any sort of hard landing will result in catastrophic failure. Of course, the carbon fiber base plates are shown here, are 4-inch by 4-inch, 2mm in thickness, carbon fiber with a epoxy resin matrix, matted by our John himself, which came out very nice. These are the prototype 3D printed motor mounts, courtesy of Lorenzo and his 3D printing, as well as the legs and mounts are fairly customizable according to whatever rod diameter we have, and also the type of motor given in with the slotted extended surface plates, which are figured right here, which would basically come out to this, our final design prototype. It's 2.25 in pounds, produces over 7 pounds of thrust, and we're approximating 15 minutes of flight time. The addition of our 3D printed motor mount shroud is figured here. And that pretty much concludes our presentation. Thank you again for joining us, and I would just like to finish regarding the totality of our experiment. We initially came in here looking to get a quadcopter working and being able to bring it to the community. And while we're still working on finishing up that process, the research and data that we have compiled, it's very, it is a wealth of information that would be very helpful to anybody who is interested in making their quadcopter. And with that, we thank you for your time.